Hi, Stanley. Oh, you're there. Good. Almost ready. We're ready. I think we can start.
Okay. Let's start. Hello, Professor. We are Group 1. Today we'll present our final pedal card design. So we have 4 parts: work distribution, pedal card overview, a subsystem, and design integration and conclusion. So first, let's talk about the work distribution. We have Harrison Tang Jing, who will in charge of the chassis design and iteration. And then Martin Weishuilai, who draw the steering system and the user interface. And then Eric Liang Yuchen, who will draw the braking system, including the wheels and also fairing and the lighting. And then lastly is me, Chen Star, and I in charge of the transmission system from pedals to rear drive shafts.
So next page, please. This is the full car rendering without the fairings. Next, please. We break the subsystem into the chassis, steering, transmission, braking, fairing, and lighting system subsystems. These are the simple CAD render of each system. Each system will be mentioned in more detail in the following section. Next, please. For engineering specification for the whole cart, we have these data here. We confirm these data based on the spaces we expect all the mechanisms to take and the grain rules of this event. We changed some of the data slightly during the designing of our cart. Now I'll pass on to Martin.
We have innovations like negative camber and differential box. The biggest innovation is that we removed the suspension system by replacing it with soft wheels. The flat race area does not require strong suspensions. By using soft wheels, it can make the pedal car less complex and easy to assemble. It can also observe the vibration in the race. Next, please. Our winning strategy is simple and useful. Maximize the efficiency. It's a 24-hour race which competes for the finish laps. So it's like a marathon, a long-term race. Efficiency is affected by distance and energy input. Our strategy is to use energy wisely to pass more distance in the corner and during overtaking. For energy used, we will take advantage of our transmission system to approach high efficiency, which will be discussed in the later section. And we will move to subsystems.
Now I'll introduce the chassis part, which is one of the most important components in the car design. Okay, next please. First is our design specification. By studying the rule and compared to the existing pedal car, we list all the specification in this table. Okay, next please. So for chassis, there are some requirements we wanted to have. First one, it must be manufactured in an easy way. And secondly, it should be able to sustain the weight of driver and other components. And beside of this, it must create less interfere with other components, and also it should be a design that could resist some extent of impact. Next, please. And before we start to design, we must know this is a sport related to human. So human engineering is important, as shown on the screen. These are tables that showing the exact ratio of each body part. So by studying this, we can have a basic understanding of what is the most efficient angle or length for the driver. Okay, next please. So based on the table, we can estimate the length and the angle of each body by assuming the height is 175 centimeters. Okay, next please. And then we can simulate it in a SolidWorks sketch. This sketch has 2 functions. One is to find the most efficient angle and length for the driver. Another function is to as a guideline for the future chassis use. Okay, next please. And for the material selection, since this it's the final material we are going to use, it has a allowable stress and the yield strength is quite enough, and the elastic modulus is also good. So which means it won't have too much deformation when the pressure is applied. Okay, next please. And in this session, we're going to check whether the structure can sustain the driver's weight and decide the minimum size of the bar. So by assuming the human weight 70 kg and the support for simple fixed point with a safety factor 2.5, and the material selection, we will choose a stainless steel. And after calculation, we can get a conclusion that the minimum diameter should be greater than 5 millimeter. Next, please. And these are two common design style of the chassis. One is open frame and one is full frame. These are the advantage here. So you can see it's easy to see that the open frame is more suitable for the pedal car. So we will choose the open frame one. Okay, next please. And these are the chassis iteration. You can see we cancel a lot of useless design from the version 1 to version 3. Okay, next please. This is the final design. Next please.
So we'll start a steering system with drawings and design process. Next, please. So before design, we create a program board to determine the overall size of our pedal car for designing the subsystems separately. The steering system is built on the chassis size. As we discussed before, we want to make the pedal car simple and light with less components. So we choose the argument steering with 4-bar linkages. Next, please. Each wheel has its own turning circle. Thanks to differential box, we can consider the rear wheels as one wheel. To achieve the highest efficiency, centers of those 3 wheels turning circles should reach one single point, which is called perfect steering, with no skidding. It satisfies the equation on the left-hand side. For 4-bar linkages, the length of each bar is fixed. By simulation, the trajectory of intersection point of each circle is not along a straight line. So it's not possible to do the perfect steering all the time in our steering system. So we make a balance to reach the highest efficiency in a range between 6 meters to 10 meters. Next, please. Steering also involves user interface. We abandoned the commonest wheel steering for its heavy and complex design with gearbox and other transmission mechanism. We choose the simplest joysticks. We use many sublime to determine the joystick size and position. We put the joints below the chassis plane to hide it and avoid intersecting with other components. Next, please. There's a small transmission in the subsystem. The joystick is a revolute linkage with 1 degree of freedom, while the 4-bar linkages are with 2. To transport the power, we use a special linkage with ball joints. Driver can easily turn in the heading direction by simply push and pull the joystick. Next, please. We add a negative camber in the front wheel for more stability during turning. We only added it to front wheel because it's a driven wheel. If we add it to rear wheels, the driving wheel, it will involve a more complex mechanism, which we don't expect. Next, please. We calculate the maximum speed when turning at the inner side of the minimum corner. By taking rolling and sliding into consideration, is about 6.4 meters per second, and it satisfies our expectation. Next, please. This is the most important performance criteria, and our perfect steering radius is about 8,700 millimeters. For engineering specification, we use aluminum as the main material in the steering system. We have a negative camber, 0 caster, and 0 toe. And now I will pass to Eric.
In this part, I'm going to talk about a braking system, which include the wheels, the braking caliper, braking disc, and the braking handle. Next, please. I'll first talk about the drawings and also the engineering specification of different parts. We are using hydraulic disc brake for our carts. This page shows the hydraulic brake actuator or handle. We designed this double piston handle to enable the rider to actuate 2 brakes simultaneously. You can briefly see how the simple linkage works inside through videos. The mounting mechanism makes use of the changing between tolerance fits. Other specification can be seen in the chart. Next, please. The braking mechanism consists of the base, which is a hydraulic tank, 2 braking pad, 2 tiny pistons which actuate the braking pad, and hydraulic nozzle and the adapter which link itself to the steering system and chassis. Nozzle linked the handle to the brakes with a hydraulic pass. It is also linked with the hydraulic tank based which link to the two pistons inside. The braking pad fits with the braking disc, providing friction. The mounting adapter is transferable to to meet different mounting methods. The material is mainly aluminum. Next, please. The front wheel are simple road bike wheels, which contain inner and outer tire rims and a central hub, which is tailor-made. The design of the wheel will minimize the ground friction. The central hub is designed to link with the disc and axis. Other specifications can be shown in this. Next, please. The rear wheel is a special design which is called soft wheel. We use this to let it perform as a suspension system. Using the 3 hydraulic pistons linked to the rim and the central hub, it can enable the axis to move relatively to the ground and the rim. The weight is slightly bigger than the front because of the 3 pistons. Next, please. The brake disc is 170 millimeter made of gray cast iron. There are 8 mounting holes in the middle and mounted with the hubs. To mount it with the hub, and others are weight deduction hole and thermal holes. Next, please. For performance criteria, there are 3 main areas. We plan the deceleration rate to be bigger than 2.5 meters per square seconds. The time using for deceleration for 8 meters per second is less than 5 seconds, and gripping force is less than 14 Newton to make the rider more comfortable. Next, please. The following is the analysis of this mechanism. After drawing the FBDs and using the hydraulic equations, applying the data using the material properties and data from some assays and experiments, we have the max deceleration 8.82, deceleration time is 3.2 seconds from 8 meters per second, and the gripping force is 36 Newton. All the data meet the criterion mentioned above. Next, please. We also did 2 simulations of the braking disc. Temperature distribution of the disc using data calculated in the previous slide show the max temperature is around 70 degrees Celsius. Following up, the thermal stress simulation shows that all stress are under the yield stress of the material, which means that there will be no structural failure. So now I'll pass on to start.
Thanks, Eric. So the transmission system is very similar to a typical bike transmission system, except just I double the rear drive wheel into 2 and add a differential between them. So I divided the drawings into 3 parts. The first is the input port, is the pedals and the front derailleur. So this is the typical pedals with 3 chain wheels on it, and there's a adapted front derailleur with metal string control. And then it's the output ports, the rear derailleur and the torsion differential. So the torque is passed from chain to the 7-speed sprocket, and then through the ratchet, the torque is passed to torsion differential to differentiate the torque into 2 rear drive shafts. And the rear derailleur is also adapted and metal string controlled. And the control input is the shifters with pedal shifters design, and the chain is using a standard chain with sprocket that can guide the chain under the chassis. The engineering specifications have 2 lookup tables. The first one is the gear ratio from chain wheel to sprocket, and another one is the gain ratio at the pedals to the rear drive wheel. The materials, they are all using 6061 T6 aluminum alloy, and the chain is ISO standard 1/2 inches chain, and the shifter is pedal control with metal string. The torsion differential has better performance than open differential if there is a raining condition in the competition, and the ratchet is supported. There are 3 main performance criteria. The first one is acceleration from stationary, and then maximum speed at highest efficiency, and lastly the cornering efficiency at minimal turning radius and highest speed. So the data analysis will all based on this diagram, which is very important. The acceleration, by assuming this data and the operating point at stationary, I got a 2.6 meter per second acceleration, which is very good. And then alternatively, if we use a fixed gear ratio with 44:16 gear ratio, the acceleration will be only 0.9 meter per second, which is much smaller than our derailleur gear because we can have 1:1 gear ratio in derailleur gear. And the maximum speed, by assuming the operating point as the max efficiency point, I got a 43.2 km per hour, which is very fast. Alternatively, if we use the fixed gear ratio, the maximum speed will be only 30.8 km per second, which is not that bad, but still not good enough. Notice that if we have even if we have maximum speed, we still have potential to go faster to overtake. The cornering efficiency is the calculation by assuming that we are using direct drive. That is, the 2 rear wheels must have the same output force. So all the centripetal forces come from the frictional force at the 2 front wheel, and then we got the efficiency of only 54. And if we use the differential, the rear 2 drive wheel will have different torque to help us to turn our pedal cart, and we get a much higher efficiency.
You have 4 more minutes.
So I'm going to talk about fairing part. The purpose of our fairing is to reduce the air friction during moving. The above show the flow simulation of air around the fairings. In this simulation, the air friction is only deducted by 0.1 Newton, while it also increased the weight of the cart. Our design does not perform well. The fairing is also restricted by the total size of the cart and the space needed to clear out for the front wheel to turn. Due to the data we collected and all the issues above, we do not think that the fairing designed by us is a must for our cars. Maybe with more study and knowledge, we can design it to perform better. Next page, please. We do not want extra weight and extra battery for the lighting, so we use commercial headlights and rear lights. This is convenient and it can last up to 12 hours and allow quick changing of the battery or the light. Next, please.
Okay, so now it's the last part. So for the integration, we use a lot of aluminum shell mostly, and then we have also stainless steel at some place that requires high strength, and then we also have carbon fiber, rubber, and plastic at some other places. For the tolerance at components fabrication, we use all clearance, transition, interference fit, and notice that we use clearance the most because we want them to be movable. And the tolerance at the subsystem assembly, for the tightening fixtures, we need to have interference to fix the derailleur, brake pedals, and the shifters. And for the steering and handles and pedals, we want them to have enough space between the drivers and the chassis so they can move freely. And the brake pads need to have enough tolerance if we don't want to brake, and then it must be interference fit if we want it to brake. And then lastly, we met all the requirements in the game rule, and we draw our design in SolidWorks with great detail, and we have good performance in many criteria. We design our pedal carts with a lot of ISO standard parts that we can manufacture or buy them directly. And lastly, with integrated design, we make it strong and light. And then that's all. Thank you.
Thank you.
Thank you.
Looks good.
Thanks.
Next group